Right, recording is starting now, and I'll start sharing. Hopefully my connection is not as poor as it thinks it is, but there we go. All right, so let's begin. So what we'll be taking a look at today is composition and delegations. That's basically, we looked last week at the existence of having a single class and object in our systems. And basically, we were focused entirely on the idea of encapsulation, which is the combination of data and the operations legal on those data into a single entity. And then we now are going to extend that idea to how do different classes relate to each other in different ways. And one of the standard kinds of relationship that exist between objects is that of containment, so also referred to as a hazard relationship. It has different forms. Some of them are a bit stricter than the others. So basically, as we'll learn in the theory, you can look at it as what we call a whole-part relationship, where the thing cannot be meaningfully defined without the things it contains. So potentially, for example, you are made up of organs. You can't really exist without organs. Your existence as a biological human being is defined by the existence of your organs. And when you cease to exist, your organs also cease to exist. So there's a sort of life cycle management as well, linking the two. Whereas if you look at a bookshelf and the books that are on it, the bookshelf can have books, but the books could be taken away and the bookshelf will still exist. Likewise, a pond or whatever could have ducks, but if the pond dries up, the ducks just move to another pond. There's only a very weak containment relationship between them. So we call the strong containment relationship a composition relationship, and the weak containment relationship an aggregation relationship. We're going to focus mainly on the strong containment relationship because that requires more work from us, in the sense that we're going to have to manage the life cycle of the things we contain. And in addition, we're going to make a point of allocating those things on the free store to force us to manually manage their life cycles as well. You can define the contained objects very often as just regular stack allocated objects, which is very easy because then their lifetime is automatically managed. But we're going to do it manually in order to get that idea across. As well as one of the reasons why we might create a system through composition is that it allows you to create these reusable entities that you can use in other contexts. So for example, if you think of a student that has a calculator and you ask the student to do some calculation, the student can't do it, but they instead ask the calculator to do work for them. The calculator gives the student the answer and the student gives the lecturer the answer. The lecturer doesn't know that the calculator did the work for them because the student did what we call delegate the work to the calculator. So it got the calculator to do work on its behalf. So that's what we're going to focus on today. We're going to focus on same problem domain as the previous tutorials. We're going to make a UJ image and we'll do it again from scratch. Just like we did with the games, we'll repeat a lot of the building steps so that you get familiar with them. And then we're going to basically have the drawing operations and the conversion operations be done via composition and delegation to separate classes instead. So that's the idea. And then just also a hint for what it's worth for the practical for this week. Don't be confused by the fact that it's called a vector. And it's got nothing to do with the vector container type, hash include vector. It's unrelated to that. And also, if you read what you actually need to do for your question, you don't need to understand any of the vector mathematics. All your vector field is a 2D array of structures. Each structure has two values, a magnitude and a direction, and that's it really. So it's in effect not really very different from an image. An image is a container around a two-dimensional array of three tuples, red, green, and blue, whereas your vector field is a container of a 2D array of pairs. So it's actually simpler in a way. And all you need to do in terms of outputting the stuff for the moment is just to output the magnitude values and the direction values, which are just real values. We haven't even given you any range constraints or anything. So it's quite straightforward. Don't let the problem domain scare you. And I think that's part of programming in general. As a programmer, you'll find yourself writing programs in a variety of different problem domains, maybe finance, maybe physics, maybe you'll work game development, maybe you'll work mobile apps, maybe you'll work in embedded devices, maybe you'll work in something that doesn't exist yet. Who knows? So a lot of the job is to sort of filter out the complexity and focus on only the parts of the solution that are necessary to get the job done. It's a kind of abstraction in a way. So that's what we're going to do. So firstly, let's build ourselves the skeleton of our image again. So remember, for every type that we've got, for every class, we're going to have a separate header field, a header file and CPP file. So for ujimage.h, we're going to have the definition of the declaration of our uj image, and its corresponding full definition, its implementation, is going to be inside ujimage.cpp. And as with libraries and everything else, we just link everything together. And likewise in main, eventually, we too will bring in our UJ image. All right, so nothing's difficult about this. What we're going to do, we're going to create our class for UJ image. It's going to be, once more, a wrapper around structures. These structures will be color structures, red, green, and blue. But what we're going to do slightly differently this time is we're going to convert not to ppm, the color format. We're going to have a conversion function that will convert to pgm, the portable gray scale map, which is just a variant of ppm, the portable pixel map. But instead of 3 values for each pixel, it only has a single intensity value showing how dark or how light that particular pixel is. So that's what will be different in this one. We will delegate the task of converting to grayscale to a grayscale converter class that will do the work for us. So let's just have our colors, red, green, blue. And just to remind us about when we use structures and when we use classes, our rule of thumb will be if it's just behavior, sorry, if it's just data, we will use a structure. If it's data and behavior, we will use a class, because any restrictions and rules about colors are imposed by the UJ image class, not the color itself. We will use a structure for the color and a class for the UJ image. Remember, once again, our convention is to start with public and then have private, because the readers of a class read from top to bottom. There are other conventions which you won't be punished for using if you use them consistently. Some people prefer to start with private because it is the default, and if you do look at a UML diagram, that's the order in which those compartments occur. The attributes will tend to be private, and they will tend to be first, or they will be first in a UML diagram. So people sometimes code so it looks more like the class diagram, and there's nothing wrong with that. It is reasonable. So as long as you're consistent, that's fine, but we use the one that we specify for the reasons we specify. We'll have a constructor where we will be able to specify the rows and columns. We'll have a constructor where we will specify everything. And the color, default color. Default, so that's going to be the color. And I suppose we could also have a UJ image where we specify the color, but not the size. Okay. As mentioned before, we will keep the attributes private. So for the dimensions, that's rows and columns. And the actual data itself, that's going to be the two-dimensional array of colors, or pixels. There will be now, for our composition and delegation-based UJ image, another class that we keep private, another pointed to an object that we keep private, but we'll add that later after we've created that class. But that too will appear here as an attribute. Because there's at least one pointer-based resource that we need to manage, or just resource we need to manage. So what do we mean by a resource? We mean something that follows the acquire, use, release usage pattern. So memory we ask for with new, we use it by dereferencing pointers or indexing into arrays and reading and writing values and so on, and we release it with delete. So it needs to be managed by the UJ image class. So the thing that will manage it will be the destructor, or the thing that will release it will be the destructor. And because we have a destructor, we automatically also need a constructor. There's actually a special rule, which we know 2/3 of at the moment, where if you have any one of these things, you need all three. So if you need a destructor, you have to have a copy constructor. If you have a copy constructor, you have to have a destructor. And later on, we'll learn about the third component in this rule of three, which is known as the overloaded assignment operator. But for now, it's just a rule of two. If you have a copy constructor, you have to have a destructor, because it means there's some resource that needs to be duplicated or deleted. So here we will have our copy constructor, taking in a UJ image reference to be the original. Okay, we will have some some accessor methods. So we will get the rows. Those can't modify the size of the array. None of the state of the object is going to be changed in any way by them, so we can label them as const functions. And we will also have one to retrieve a particular pixel at a particular location. So we'll call that getPixel. Take in a row, and it's going to take in a column. And it's not going to change anything, so we can label it as const. And then we will have a mutator for setting a particular pixel. We're not going to make the array size resizable, so we will have a void member function for that, which we will call setPixel, and it will take the location of the pixel we will change. As well as the actual value we're going to set at that location. Pixel, and it won't be labeled as const because it will change the contents of the array. So that's fine. And then what else do we need? We need a conversion function. So in this case, we'll still call it, let's just call it, I mean, technically PGM is a kind of PPM. So we can still call it 2ppm, I suppose, but I'm just going to call it toString. Maybe, yeah, or convert to string, just to not introduce any inaccuracies. But either way, we're going to need a string data type. We can use the standard namespace if we want, but it's considered bad practice in a header file. So instead, we're going to fully qualify the return type of this function. std, scope resolution operator, string, and let's call it, let me call it convert, because the string, convert to string, because it's going to have the work done for it by our internally managed converter, which we don't have yet. We'll add that later. So for now, it will just be a dummy. So I think that's all we need for now. Is we also wanted a drawing function. I suppose I could just, yeah, let's do it. I could just draw in main with setPixel. Let's not make it too complicated. So that's fine. All right, let's begin. We also, since we're at it, probably a good idea to think about enforcing the logical properties of the data type. So what are those properties going to be? They're going to be, that's the different things will be inside a particular range. So we're going to have a value, and some minimum and some maximum. Max value doesn't really matter, but that's not going to actually modify anything. It might end the program, but it technically won't be modifying the state of the object, so we can label that const as well. And yeah, I think we're good to go for now. So let's start implementing these things. Right. Oh yeah, one thing we do also potentially need, or would certainly be helpful, is to have a set of class constants to represent our defaults and maxima and minima and whatnot. So let's have a static const. Remember, static means there's only one copy in memory. Const means there's it can't be modified. And an integer, let's go for max size, however big that's going to be, and a minimum 1. And I think that's all right. I suppose we could also, if we wanted to encode it explicitly, we could say max color 255. All right, so there we have our class. We don't need to copy the static constants into the CPP file. They're already defined in the header file. And then we're going to start implementing our image. So remember the member functions, implementation CPP file. You have the fully qualified name of the function, which means that it's got the class name in front of it, because the class kind of acts like a namespace for its member functions. So for constructors, that means it goes at the beginning. And for the other member functions, it goes after the return type before the name of the function. So for here, don't just paste it blindly at the beginning of the line. Include the const, don't delete that, because technically speaking, you can have two versions of a function, a const version and a non-const version, and so that you can call it under different circumstances. You can always call a const function in a non-const context, but you can't always call a non-const function in a const context. So if it's const, it doesn't really need another version, but sometimes if you've got slightly different logic when something's being called in a const context, then you can have two different versions of it. Okay, destructor. Utility function. All right, that is that. Technically speaking, we don't need to fully qualify the name of the string there, because in the header file it's bad, because that will, or using namespace standard is bad because it will pollute the namespace. But inside the implementation file, that's not the case. So, because no one includes the CPP file, they only include the header file. So you can happily bring in the standard namespace all you want there. So things we might wind up using, we're going to output, so IOStream. I believe at some point we'll probably need to do some conversion. Probably need to add a function for that. We got our string stream. And for now, that's all I can think of. I guess maybe assertions if we wanted to be extra safe, but even then we might not really need to. I suppose one thing we could also add to our header files, we could have an enumeration for our status codes and success. And I guess our two range errors are likely. So if the range is too high, the value is out of range in the positive direction, or if the range is too low. Okay, did we set min size of 1? All right, so let's begin. If we look at the different constructors, the one that probably winds up doing most of the work is the fully qualified, fully parameterized constructor, the one that's got all of the parameters, and that way we can use it to do most of the work. You can, of course, repeat the work in all the other constructors, but that's not great because if there's a bug, you'll have to fix it everywhere, and you should try and not repeat yourself. There's a philosophy in programming called DRY, D-R-Y, don't repeat yourself. So we'll try and do that. I'm just going to check if there's any questions. So hopefully that's been addressed, but we do have rows and columns. If I've made a mistake with that, hopefully we'll see it soon. Do we always have to have the max? No, you don't have to have that. I'm just using it as it's a good example of something that you might want for a class constant. So I'm just using it as an excuse to revise how class constants work, that you use static and const inside the class. So that's all. You don't have to do it that way, of course not. But there's nothing, I mean, having named constants is incredibly helpful. So previously you set the function pointer of the pseudo object to a reference in the CPP. Yeah, so yes, basically, C++ does all of that nasty hard work for us when we specify that it's a member function with the scope resolution operator. So it automatically adds under the hood an extra parameter at the front called, well, maybe not the constructor is not the best example, but let's say for get columns, it automatically adds an extra parameter there called this. It does it with constructors too, but anyway, called this, which is of type UJ image pointer. So that nasty work is all done and automatically binds the implementation functions to their prototypes in the class. So all of that nasty work we did manually gets done automatically for us. That's exactly correct. All right, so let's begin with the fully qualified constructor. Let's check to see if the rows and columns are in range. So we said that the minimum was going to be 0, oh no, 1. Actually, we've got a constant for that, so let's use it. So and maximum and our value. I feel like I normally do the value at the end now that I look at it, but it doesn't really matter. So we've done that for rows, done that for columns. Now that rows and columns have been safety checked, we can safely allocate them. Okay, now that we've got our rows and columns set, we can start to create our array. Create the outer level of the array. As big as the number of rows for every row. Create the inner row array, which is as big as the number of columns. And then for every column, set that equal to its default. So pixels at position row and column is equal to our default color. And for now, we're going to have to come back and edit this in a moment. I think that's everything we needed set up for us. So that's good. I suppose we should also do a safety check on the color. Let's do it because the red, green, and blue values could be out of range. So between 0 and 255, let's check rec color red, green, and blue. Now it's impossible to create a class that doesn't match the rules. We'll also impose those constraints in the mutator function for setting color manually, as well as accesses to make sure that we don't reach outside of the array. But for now, we've got our main constructor that does most of the work. So this one here will just use pure default values. As I said, refer to this as the no-args constructor, but many refer to it as the default constructor because it initializes the values to their defaults. Everything's a default, but not to be confused with the free version of this you get by default if you don't specify another one. So no-args constructor, just to be consistent. And then what are we going to do? We're going to delegate to the other constructor using the constructor delegation notation. Another way of doing this, because for what it's worth, constructor delegation is a reasonably recent addition to the language. What people would sometimes do is they just have another helper function called setup or init or something like that, and they would just call that function in the various other constructors, which you can still do if you want. It's actually quite readable. I don't actually like the look of this syntax. I think it looks ugly, but it is the standard. So that's life. So this one will have default rows, default columns, default color. So what are we going to do? Default rows. So did I make a default? I don't think I did. Let's do it. Good example. Default rows. And default columns. Okay. And default color, which I'm just going to use the initializer list for structures here, and I'll just set the default to a white image. I did white last time. Let's do a black image. It's also easier to see when we test it. So 0, 0, 0. So that's all the work done there. Inside this one, same story, except we'll use the value specified for rows and columns by the user, but still the default color. So UJ image, the rows that the user sent, the columns that by user I mean the programmer, the client programmer, and then the default color, which we will have as 0, 0, 0. You could actually make a static const structure if you wanted for default color as well. That would work. But I do just want to remind you that you can use initializer lists for structures. So this is just an opportunity to do that. Here we've got a color coming in, but no sizes. So we'll use the default sizes. Default rows. Default columns. And the color that they specified. So that will be color. Okay, no further work to do inside there. This one's already implemented, does all the work for us. Here we've got the copy constructor. So its job is to make a duplicate of an existing object. So what we do is first we just make sure that we're going to be exactly the same size as the other object. So we will delegate off to another UJ image, and we will just steal the size of the original so that we can be the same size as them, which will make copying easy. So we'll take their rows and we'll take their columns and make ourselves exactly the same size as that. Original. Notice that I don't have to use the accessor functions. I don't have to say get rows and get columns. Why is that? Because original is not me. It's someone else that I'm copying. And the answer to that is that the public and private and protected levels of visibility are enforced at the class level, not the object level, because the idea being that you are the author of the class, so you should know what you're doing here. So basically, that's why you can skip get rows and get columns. You could still use get rows and get columns if you wanted to. It would still work, but you can bypass it within the class. And so once this is executed, once the actual braces here start to run, the code between those braces starts to run, this delegated constructor will already have finished. So now we just need to do the remaining work of making a copy. And that remaining work is simply to loop over the original and copy their pixel values into us. Nothing complicated. So for every row, and we know for a fact it's going to be the same size as us because we just copied them in terms of size, and the array got allocated correctly. For every row and every column, transfer into our pixel array at position row and position column from the original. We can also skip get pixel if we want to, and just reach directly into their pixels array at position row and position column. And there we have it. So now once this is finished, we will be a proper deep copy of the original. For getting the rows and columns, those accesses are super easy. We simply return rows and return columns. Much needs to be done there. For get pixel, we do need to do a safety check just to make sure that the index is valid. So kind of like this, except we're checking. I don't even know if it's worth copying that. Let's just do it properly. So we're going to enforce range and make sure that between 0 and rows -1. Yeah, definitely did it the other way around the last time. It looks weird this way. But anyway, rows and column. Now we know that it's safe to touch the array. And remember, a lot of the errors you guys get when you see things like segmentation fault or just exiting with some very high error number, or some of these very difficult to isolate crashes occur because you touch the array and reach outside the array's legal bounds. So by using a UJ image class like this, at least you'll get a proper error message telling you that there was a range error rather than just some random segmentation fault crash. So that's part of the advantage. Here we're actually setting a pixel, I see, so we actually also need to test to make sure that the pixel's values fall within range. I could probably have delegated that to a validate pixel function. I think I did that last time, rather than repeat this. But anywho, and now that it's safely been tested, we can stay inside the pixels array at position row, at position int row, position int column. You will set for whatever reason, in my wisdom, the rec pixel, and that's that. Okay, I skipped get pixel. Get pixel will basically be the same idea, except we just need to check that it's within the array, and then reach into the array, but we're not going to change anything. We're just going to return that value. And okay, convert to string and the destructor we'll look at in a moment. Let's just quickly do enforce range. So that's simply going to be if value is less than n, error message saying too low value less than. Actually, let's keep it short. I think it'll just be enough to see that is less than int min. And we can exit error code for that. So range low. And likewise, if it's too high, it's greater than max, then and we can exit with error code for that. That seems reasonable. And then lastly, but it will need some modification in a moment, the destructor. At the moment, the only resource that's being managed by UJImage is the array. So all we need to do is to loop over every row. Delete that row array, delete the outer array, and we don't even have to worry about setting things to null because the entire object will cease to exist in a moment. So before I look at conversion and what we're going to do differently this time, I'm just going to go back and see if there were any more questions. Okay, so here we go. I used green twice. Whoops. Thank you. Good job spotting that. Green and green, so red, green, blue. And then due to the wonders of copying and pasting, rather than having a validate pixel function, I'll now have to hunt that down as well. Well done. Okay, that's good. Good, good, good. Yeah, thank you. Okay, a couple of people saw that. Where are you going to use the max size color? Did I not do that? Did I define that? I did. Oh, that's silly. Yeah, I may as well have used that inside. Oh, again, should really have just done a. If you end up doing this more than once, then your life is telling you something. So we're just going to do a validate pixel. Color. Okay, and we're going to implement that. Should have done that from the beginning. Really matter the order I do it, but same. Do it properly once. Don't repeat yourself. Stick the non-broken version of this in. So we'll fix you. Here. Let's just do it well. Okay, and all right, red, green, blue, and then the other place where I do that for a pixel. Here, let's just go validate pixel. And there we have it. Okay, so that is better. Let's see where else there were. These were good suggestions. Since I set rows and columns within the constructor, would the idea of setting them in separate functions require more work? So these functions for set, okay, so for what it's worth, if you mean if we have the ability to set rows and set columns, that's quite a big impact on how complicated this class is. Because if we shrink the class, then we need to, well, basically what you need to do when you resize it is you'd need to allocate a new array, copy everything from the old array into the new array that fits within the new array, because so obviously if the new array is smaller than the old array, you won't be able to copy everything. And if it's bigger than the new array, you would need to set defaults for those things. So it becomes a lot more complicated. So we're basically making ours immutable in size after you've created it for the first time. So yeah, that's the reason why we're doing it that way. Would it be considered good practice? That depends on what you want to do. So like a vector resizes, but the built-in on the, what would you like to say? There is also a type in C++ called array, hash include array, which you use kind of like a vector. So let's say array of size int, but it's, and this ARY stuff, oops, size 10, and it's not resizable. It's like a vector, but it's fixed size. So it's nothing wrong with having things be fixed size once they're created, and to keep things manageable. That's what we're doing with our images. We might, in a test or in a practical or in a future tutorial, have a resizable image, but it is a lot more complex than an image whose size is only set once. Yeah, so that's the reason for it. All right, so what we're going to do differently now for the conversion. Firstly, we're going to convert to grayscale. Not that that's super interesting, but we're going to have the work be done by a class that the UJ image has. It will contain it. There will be a has-a relationship between the two. So if we take a look at what the design would look like, let's do that. All right, so let's switch over to the design, and let's do a design for our UJ image. It's going to be a UJ image. It's going to have a rows of type integer. They're going to be private. It's going to have now columns of type integer. They're going to be private. It's still going to have its array, and we're going to keep this at a sort of low-level design, so it's okay for us to say pointer pointer. Oops, that's the type, sorry. And that will be pixels. So general, you could say something like 2D array, which isn't a real type, but isn't specific in C++. 2D array or color 2D color array or something, but it's okay. Let's keep it low level, and that's also private. And then we're going to have as well all those constants. So max size, that's integer, it's scope, it's public, so that's fine. And then min size, and we can even set the values there. So what was max size? 10,000 or whatever I said. Min size is 1. It's a const int, and const int. Static class scope. I'm not going to do all the rest because it's just a lot of duplication, but you'd add the rest as well. So those are the attributes. Then we've got the operations. So image, that's the arts constructor. We will have UJ image with some parameters. So that will be the one where we specify rows of int, columns of type int. And then we'll have the other one where we specify the size. And that's going to be, so we specify the size, we specify the color, so that's color of type rect color of type color. And then we're going to have the copy constructor, obj original, it's going to be a const. This, you could say a const reference. It's not really C++, or we could name it like that, I suppose. It does really affect the type, but that's fine. Anyway, now then we've got our accesses. So we've got our get rows, int, get columns of type int, set get pixel, color, which will take in a row of type int, and a column of type int. And then set pixel, which is going to be void, take in a row, int, column, int, and a pixel or whatever we called it of type color. Right, and then we will have our conversion function, which will give us convert string and the parameters, and then we will have our destructor. And we have our private helper functions here. So we have our enforce range, which is going to take in, for whatever reason, min first, max next, and value last. Then we also had our parameter, but then we also had our validate pixel, took in pixel of type color. So for our single case, a single class, this is our UJ image. But now what we're going to do is the way we're going to implement the convert function is we're going to get some other class to do work for us for that using composition and delegation. So we're going to have a converter class here. It's not going to really have that much inside it, to be perfectly honest. So really we're just going to give it an operation. That's going to be the convert function. String back. And now what's going to happen is the UJ image will have one of these. So here is our containment relationship between the two. And because the UJ image has one of these, we could even specify if we wanted. Oh, that's, did I pick the right one there? No, whoops, similar but wrong notation. This is the one I wanted. There we go. Then we want to specify it's a strong has a relationship, so composition, because this thing is going, the UJ image is going to completely manage the life cycle of the converter. And then we can say the multiplicity as well, that in this case it's 1. And now, because the UJ image has one, it needs to have a variable of that type as part of its attributes. So we will add, and let's do it manually, we'll do it with pointers. So let's have a converter, of type converter pointer. We'll keep it private. I'll put the other private stuff. And now that's what we've got. So there's our converter, there's our has a relationship, and the convert function here will actually be realized by the convert function in the converter. So that is our, it's going to take a long time to draw there. Oh, well, you can see it here. There is our converter function and a convert function which will be delegated to the converter. So we're going to need to make some changes. Inside the constructors, we're going to need to make sure that the converter gets created. Inside the destructor, we're going to need to make sure that the converter gets destroyed. In the call to convert function in UJ image, we need to send the work off to converter. And obviously, we need to create the converter to actually do the work. So for now, let's just create a skeleton for it. But before I do that, I'm just going to check if there's any more questions. Yeah. Okay, in terms of the... Yeah, look, so the vectors we have at the moment, I'm assuming you're talking specifically for the practical on Friday, your vectors just contain 2 values, direction and magnitude. If you wanted to do things to represent a set of points, you could of course do that, but the description you were given is that each vector contains 2 values, magnitude and direction. However, you will have a 2D point, a 2D array of these vectors. So basically a 2D array of structures, each structure containing a magnitude and a direction. So there we go. Could I use a modified copy constructor to resize a member? So there's nothing stopping you creating a constructor that does that. It wouldn't be considered a copy constructor because by definition the copy constructor has exactly this signature. But of course you can create a constructor that takes in an original and a new size for it and does the resizing for it. You could call it a resize constructor if you wanted. Absolutely, there's nothing physically stopping that. What is class scope? Good question. So class scope, if you saw that in the design here, when I clicked on for here, class scope, that means static. Right, so very good question. That in C++ terms, static means that it has class scope. If it's inside a class and use the keyword static, that's what it means. Very, very good question. Thank you. All right, let's carry on. So let's build the skeleton of our converter. So it's going to be its own class. It's going to have its own header file. We'll keep it very simple because we're focused more on the idea of composition and delegation than keeping things super complicated. So the converter got a header file. Inside here, we'll define the class. Sorry, the class convertor. And it's going to really, this is very simple. And it's just going to have a string and convert. To be honest, you really wouldn't need a class to do this, but as I said, keep it simple and include string. And then to implement this incredibly simple class, we will do that now. But first, let's just get the skeleton up. So we make a CPP file for it. .cpp. Okay, get to the header file. This is where we'll put our logic. But there, I see I've called things convertor and converter. Let's be consistent. What I call it in my design. Yeah, there we go. All right. And we'll put the details in a moment. But for now, let's just focus on the actual composition and delegation. So because this thing has a converter, it needs to know about the converter type. So we can do that. So it has a converter that it's going to manage. So we'll do the management of its life manually. So we'll allocate it with new and delete it with delete. Okay. And now we need to modify the constructors and the destructors to do that. Now, we could put a creation thing for the converter in each of these constructors, but that's silly because we want to minimize the amount of code we repeat. So let's just make the one constructor that sort of gets used by all of them be responsible for allocating the converter. And then we know for a fact that it's always going to happen. So we're going to say here in our converter, we'll create you as a new converter. And obviously, likewise, it's now a resource that we're managing. In our destructor, we need to get rid of it. And the actual act of delegation, the idea is that the UJ image won't do any of the work. It will simply ask its converter to do the work for it. So instead of doing anything difficult, it's simply going to say, converter, you do the job for me. And by that, that just means I'm going to call your converts. I did not name these consistently. Right. So this is the act of delegation. So let me label things as we go on. This is composition. This is life cycle management, particularly for creation. And then over here, this is delegation. and this is lifecycle management, but on the destruction side. Okay. So now all we would need to do is to actually just make the converter do something, which, to be honest, that's got nothing to do with object orientation per se, but for what it's worth, if we wanted to convert something into, into a UJ, into a grayscale map, we don't even need to include the IO stream, or the SS stream here, because all that work's going to be done in the converter, in its implementation. Oops. So what it's going to do is it's going to create a grayscale map. So the grayscale version of PPM is simpler. Instead of having a red value, space a green value, space a blue value, it simply has one single value that represents its intensity, and you can also just use a number between 0 and 255. And then how do we convert a color image into grayscale? One of the easiest ways of doing that is simply to add the red, green, and blue values together and divide that by 3, and then that's left with the average of it. It's not the most sophisticated grayscale conversion algorithm, but it's straightforward. So before I implement that, let's just see if there's any more questions. Okay, so this is a great question. Why did I say that it converts a pointer instead of converts a pointer? This isn't a 2D array of converters. It's one single converter that we've allocated on the free store. So it's not an array. It's one. It's like basically going new int. Not new int with square brackets. I just want to allocate its memory in the constructors and deallocate its memory in the destructors. It's simply it's kind of like the pseudo objects that you used earlier, where you created a new pseudo object image and then deleted it later. It was a single pointer, not a pointer. So good question. Okay, perfect. All right. How can I understand comp science clearly? So the computer science is like learning to play an instrument, or learning to play a sport, or learning to anything that requires skill acquisition. So you have to practice. The only way to do it, you have to work through these tutorials. You have to work through the practicals yourself. As much as it's tempting to get help from other people, your friends can't help you properly. So if you do have questions, ask them on the Discord. It will be very difficult at first. You'll get it wrong a lot, but that's how you learn. Just like if you started to dance, or you started to swim, or you started to play a sport, you'll be terrible, right? Until you're not. But unless you work through it and put in the effort, it's not going to get any better. You can watch all the fitness videos you want. You'll never lose any weight by watching it. You have to do it. Okay, so that's a good question and an unfortunate truth. All right. Anyway, so now we've got the lifecycle management and all of that going. So this is the actual implementation. This, to be honest, really hasn't got anything to do with object orientation per se. But let's make for ourselves a string stream, SS, PPM, PGM, I guess. Portable grayscale map is technically what it is. At the end of the day, we will return that, but convert it to a string. So for what it's worth, the grayscale version, let's make a note that this turns to grayscale. Converts to grayscale. That has P2 as its magic number. So P1 is a black and white image, just pure black or pure white for each pixel. Grayscale can obviously have shades of gray, and color is obviously with color. So it's P1 for black and white, P2 for grayscale, and P3 for color. It too will have its dimensions, which will be the column. Ooh, this is interesting. Yes. Excellent. This is going to be slightly more complicated than it looks at first. What we're going to have to do for the converter here is it needs to know the details of its image. So one way to do that, and this is why we do this, is to have us pass the image as a parameter. It's going to cause some interesting interesting collisions here. So let's just do that. So this thing needs to know about the UJ image. Otherwise, what's it going to convert? So let's add that as a parameter. It's going to need to know that as have that as a parameter, but it's going to cause a little bit of a cycle here because the UJ image needs to know about the converter, but now the converter also is going to need to know about the UJ image. So this can be fairly tricky to break, and this is why we artificially induce this problem. So let's trigger the issue. Okay, this doesn't do anything yet. We'll actually fix this later. But let's see if we can even just get this thing to compile first. So for now, the convert function is not going to do anything, but let's just see if this will compile. So let's compile. And it doesn't know what's going on because it sees a converter here, and it says it doesn't name a type. And over here, it says, I see a UJ image, and it doesn't name a type. And the reason for this is we've got a, why are you weird? It's not an error I expected. Oh, because we didn't add the references, the parameters here. Fine. So that'll go away, but we'll still have the other two errors. Oh, come on. Fine. Okay. Again. Right. Now we've got this situation. The UJ image needs to know about needs to know about the converter, and the converter needs to know about the UJ image. How do we break this cycle? So the one way in which you can do it, think about how you did it with functions. You might have that same problem where a function needs to know about another function in order to call it, but maybe it's a pair of mutually recursive functions, so they need to know about each other. Or even just if you put functions before you learned about header files and libraries, and you were just writing functions inside main, you'd have to be very careful to make sure that you declared your functions in the right order so that the ones below can use the ones above it. So how did you fix that? You fix that with the function prototype, which is basically just a promise to the compiler saying, I'm going to give you a full implementation of this function later, but for now, just calm down. And the question is, can I do the same thing with the class? And the answer is yes. You can create what's known as a forward declaration of a class. It's just like a function prototype, but for classes. It's basically a promise to C++ saying, in the future, before you finished compiling this program, you will find an implementation for this class. But for now, calm down. Everything should be okay. So hopefully this will solve it. So the way in which you do that is you simply use the class keyword, you give the name of the class and a semicolon. And that's basically saying, I promise you C++, don't worry when you see a converter here and you don't know what it is, because later on we will sort that out. So hopefully that'll be enough to break the cycle. Let's see. Okay, we've still got a similar image here with the UJ image. Hopefully if I do another class forward declaration, that will sort that one out. Oh, okay, and here, okay, perfect. So that you can see that did break the cycle. We promised UJ image, or C++ will tell you what a converter is later. We promised converter will tell you what a UJ image is later. Now that problem has gone away. The only thing we've got here is we need to actually pass ourselves to the convert function so it can have access to our data. So what represents us? The thing that represents us is the keyword this. That's the equivalent to the object self we created with the pseudo objects. But, and I did this deliberately to just give us some practice, what type did we promise here? We didn't say a UJ image pointer. We could have, but we didn't. We actually said a UJ image reference here. So how do I convert from a pointer to a value, you simply dereference ourselves. So basically what this is saying is pass myself not as a pointer, oh wait, actually automatically take me as a reference instead, and then carry on from there. So hopefully this will at least compile now. Other problems. Not one I expected. Oh, simple problems. Okay, I probably copied and pasted, so that's not my fault. Okay, hopefully those will go away now. Oh. Easier. Okay, compilation. So the reason we do this example the way we do it is to sort of trigger these problems so that when you trigger them in your code, you know what's going on. So let's just recap what the idea was. The idea was a UJ image has a converter that does work for it. A converter needs to know about a UJ image in order to get the information it needs to do the conversion. So we hash include UJ image inside converter, and we hash include converter inside UJ image. The problem is that this is cyclical. The UJ image needs to know about the converter before it can be fully defined, and the converter needs to know about the UJ image before it can be fully defined. How do we break that cycle? We use what's known as a forward declaration, where we just say, I promise you C++, there will be a class called converter at some point, calm down. And likewise over here, I promise you C++, at some point there will be a class called UJ image, calm down. And then you can see that it's at the end of the day, it finds full implementations for both of them, and the cycle is broken and it compiles. Now we can just easily implement our conversion function. So we wanted the size. Now we need to access the rows and columns. That's what our accessor methods are for. We can't reach inside over here and just say underscore rows. Let me just try and do that, and you'll see what happens. Columns first, but anyway. Because it's private within this context. So that's the whole point, is a converter isn't a UJ image. A UJ image has one, but that doesn't give it magical access to its data. In the same way that you have a cell phone, but hopefully that doesn't mean that it can read your mind. So I think private things should still stay private, but that's what accesses are for. So we call the getCalls function, and we call the getRows function. And that will get us the initial bits. Then we just need to say what the maximum component is. That's 255. And then we need to loop over every row and column inside the UJ image, get each pixel, squash each pixel into a single grayscale value, and output that instead. So let's do it. So for every row, for every column, get that pixel, then we'll get our new intensity value, call it I, and that's going to be rectPixel.red plus pixel.green plus pixel.blue. And divide that by 3, average it into our grayscale color, and then we can simply output, not cout, but SSPPM, add I, space, and at the end of our row, add an end of line. Then we should have our conversion function done. So that's good. Now we can just use main. And the interesting thing you'll see about main, and this is part of the advantage of using the composition delegation based approach, no one who's using main, the UJ image from main, has any idea that a converter exists or exactly how the responsibilities that a UJ image has are divided up. That's the whole point of separating logical properties from implementation details. For us, this will look like just a regular UJ image with a convert function that does stuff. We don't know or need to know exactly how it is structured internally. So let's begin. Let's make our UJ image. Do I have any reason to do a different size? What's a reasonable size? I don't even know. 4. Let's even give it the default, a different. Leave the black default. That's fine. Then let's just, what I'm going to do, let's draw. I don't know. I'm not going to make it too complicated. I'm just going to draw 3 colors on it, sort of like a flag. So the first third will be one color, and the next third another. So we'll just do an image like that. So for every row, for every column, we'll just split it 50-50 even. So if the row value is less than half of the rows, we'll output one color, set it to be one color. So that will be obj image dot set pixel at position row and column, and we'll set that one to, I don't know, 1, 2, 3, 1, 2, 3, 1, 2, 3, whatever color that might be. Otherwise, if it's in the second half of the image, same story, but we'll set it to white. Something not white, so that let's set it to red. So that's not convert. That's a pixel, row and column, and red we said, so 2, 5, 5, 0 and 0. And then we've now got our image, which is half this color and half red. And now we're going to convert it to grayscale before we even see it. So what we're going to do is we're simply going to output obj image dot convert, and we should get a grayscale image on the output side. But notice the user of the class, the client programmer, no idea about the converter class and all of that complexity or that structure. It's just, they just use the UJ image like they would any other UJ image or any other class. Those details are not really the concern of the client programmer. Let's see if this compiles. Whoops. All right, let's compile again. Okay, let's run it. Okay, and let's test it. Okay, let's just see if we get any errors or see what looks like it might be an image. Okay, that looks reasonable. And let's actually output that to something which we can see. So image.pgm for portable grayscale map. And then that should exist. Hopefully my OpenOffice knows what a PGM is. We'll see. Yeah, and there you go. We converted our image into grayscale using an external converter class. Now, the important thing to note is just recap what the learning outcomes were. We wanted to learn about hazard relationships. So let's actually update this so that it can take as its parameter the image. I put that on the wrong one. Let me just check that now. No, that's fine. So the UJ image has a converter. What does that mean? It means that inside it, it will have a UJ image, a converter variable of some kind. In this case, it's a pointer variable. In this case, we made it manage the life cycle of the converter. So this is a strong hazard relationship, also known as a composition relationship. So it's got a solid diamond. If it were the weak relationship called aggregation, it would be an open diamond. But in this case, as you can see from main, the UJ image doesn't exist independent, or the converter doesn't exist independently of the UJ image. They're one and the same as far as the user is concerned, just like you and your organs are one and the same to other people who interact with you. So inside the constructors, we allocate it. Well, actually, we redirected everything to one constructor that will definitely allocate it. Inside the destructor, we deallocate it. And then when we call the delegated function, the function that it's going to do work for the UJ image, we then send that work along to the UJ, to the converter. We deliberately made a dependency, a cyclic dependency, in the sense that the UJ, the converter needs to know about a UJ image, and the UJ image needs to know about a converter. So to solve that problem, we had to use forward declarations to promise that we would implement a converter class later, and likewise to promise that we would implement a UJ image later to break the cyclic dependencies. And then in main, okay, we implemented the converter to do whatever it is that it needed to do. In this case, add the red, green, and blue values and convert to, and divide by 3 to convert to grayscale. And then in main, we just use the UJ image class as per normal. We don't have to hash include converter. That's all managed by the UJ image. And when we call the convert function, for all we know, it's being done by UJ image. The fact that it's been delegated to another class to do the work for us is irrelevant as far as we're concerned. And then we got our output, which was a grayscale image. So I'm just going to go back and see, are there any questions? Okay. What can I do to practice? Okay, we discussed that. Yeah, okay, yeah, it does work. It's really, you can do it. You've got time. This is only week 3 now, the very beginnings of week 3. If you just work consistently, everything will be fine. I promise you. Just work consistently. If you've got questions, please come to Discord and ask. We're very happy to help you. Yeah, so the general rule of thumb, it's not a hard and fast rule, is that every class will have its own header file and CPP file. But sometimes there are some classes which are so closely aligned to their UJ image, to another class, that you put them in the same header file with them. I wouldn't say a converter in this case would count, but maybe you would. But I deliberately wanted to show you the complexities of the cyclic dependency. But later on, we'll do container classes like lists, and they will have a special kind of class called an iterator, which will let you move through them. And those are so tightly bound to the container that we will put them in the same header file. So mostly. So your UJ image has a converter, 100%. That's exactly how we would describe it. Why does it have it in its own file? So say rule of thumb, each class will get its own header file and CPP file. Is the converter using the free constructor? Yeah, in this case it is the free constructor. That's not a bad term for it, because so perfect, nice observation. This converter doesn't have a constructor, so it automatically gets one for free. Just hang on, this is a good example, and we rely on that fact over here because we create a UJ image converter like so, and it must work because there is a constructor for it. But if we did something like this, let's say we created a new constructor or converter, sorry, converter constructor, and just it doesn't matter. We had one that took a parameter. We're not even going to implement it, so I'm just going to put it here. Right. I don't think I want the semicolon there. So this is now an empty implementation, but notice that it has now got a constructor, one that takes an integer. It won't get the free no-args constructor anymore. So now this won't compile. I haven't actually taken away any functionality. Technically, I've just added functionality, but we were relying on the free constructor to be added to the converter, which now won't happen because we've got another one. So this will all fall over. And it says, I can't create a converter. There's no constructor for it. So a rule of thumb, to be perfectly honest, even if you don't need it, let's just do it. It is, I believe, good practice to always have a no-args constructor explicitly, even if it doesn't do anything, just so that you don't make that kind of mistake where you rely on it getting it for free and then that goes away. So back again. So that was a great question. And then how do I know whether the relationship is or has? Well, for now, we haven't even said the word is a relationship. We literally haven't dealt with that yet. So it can only be has a because we've only done has a. I will get back to that excellent question when we've done is a. Then I'll tell you when we can distinguish between an is a or has a relationship. But for now, we've just done has a. So that's all you have to worry about for this Friday. So I think that's that, ladies and gentlemen. I'll upload the code, obviously, and we'll link the video once it's finished indexing. If there are any other questions, please ask. Otherwise, I wish you all a good afternoon, and see you later for class. Okay. All right, so I'm going to stop recording now, and see you later.